Good evening, class. Yeah. So, in today's class, I'll be solving the problems which are based on the Cooper pair problem, the superconductors. It is assignment number 11 from Electronic Theory of Solids course. Electronic Theory of Solids course, 2025 NPTEL. Okay. So, in today's class, I'll be solving the 10 problems based on the superconductors, Cooper problems, BCS theory, and will try to give you more insight on how to approach these kind of problems. Not only that, it will also help you understand the concepts which has already been discussed in that class. So having said that, I'll start from the very first question, which is like, choose the correct statement regarding Cooper problems. And the first option is the Fermi liquid is unstable toward attractive electron-electron interaction for some threshold value dependent on Debye frequency WD. Second option is the Fermi liquid is unstable toward any arbitrary small attractive electron-electron interaction. Third option is the Fermi liquid is always stable for energies beyond Debye frequency h bar omega d. And the fourth option is the Fermi liquid is only unstable for strong electron-phonon interactions. And we have to choose the correct statement regarding the Cooper's problem. Okay. So the Cooper problem shows that Cooper pair problem shows that Cooper problem shows that if you have a Fermi C, a filled Fermi surface basically, and two electrons above it interact via an arbitrary weak attractive potential they can form a bound state. Second. So they can form a bound state which is known as the Cooper pair. And that is known as Cooper pair. This implies that the non-Fermi liquid state is unstable to the formation of such pairs even for an infinitesimally small attractive interaction. And there is no threshold strength required. And this also forms the conceptual basis for the BCS theory. So this implies that the normal Fermi liquid state is unstable to the formation of such pair even for an infinitesimal small attractive interaction. There is, and ultimately there is no threshold required. Strength required. This forms the conceptual basis of BCS theory of superconductivity. So what does it say? It says that for the normal Fermi liquid, the formation of such pair is possible for an infinitesimally small attractive interaction also. So there is no threshold required. So which option says that? The first option says that the Fermi liquid is unstable toward attractive electron-electron interaction for some threshold value. So it is not dependent on the Debye frequency. The first is incorrect. Second is the Fermi liquid is unstable toward any arbitrarily small attractive electron-electron interaction. This is true. Now just let us look at the other options also. The Fermi liquid is always stable for energies beyond Debye frequency. No, it's not stable. The Fermi liquid is only unstable for strong electron-phonon interactions. Though electron-phonon interaction plays a good role in the superconducting phase, in attaining the superconducting phase, but it is not the strong electron-phonon interaction. So this is also incorrect. So the correct option which is there for this question is that for the Cooper problems, the Fermi liquid is unstable toward any arbitrarily small attractive electron-electron interaction. So this is option number 2 for question number 1. If this is clear, then let's move on to the next problem, which is the Jingberg-Landau parameter is kappa is equals to lambda L by eta L for a type 1 and type 2 superconductor. Choose the correct options. So type 1 and type 2 are given that the kappa will be less than 1 by root 2 or greater than 1 by root 2. All those things are given. Okay. So let's first understand what is this Ginzburg-Landau parameter kappa. So the Ginzburg-Landau parameter kappa is defined as lambda by eta. So lambda is equals to penetration depth. What does it mean by penetration? How far magnetic field penetrate into superconductor? How far magnetic field penetrates into superconductor? And eta is coherence length. What is coherence length? Size of Cooper pair. Order parameter. Variational scale. So based on the values of the kappa, a type on superconductor kappa is less than 1 by root. That is approximately 0.707. So they exhibit complete Meissner effect and abruptly lose superconductivity at critical field Hc. So they exhibit complete Meissner effect and abruptly lose superconductivity at critical field Hc. But, and for the type 2 superconductor, kappa is larger than 1 by root 2. Second. For type 2 superconductor, kappa is greater than 1 by root 2. They exhibit mixed state. What is this basically? Between Hc1 and Hc2, allowing partial magnetic field to pass. So for type 2 superconductor, kappa is uh, greater than 1 by root 2, and for type 1 superconductor, kappa is less than 1 by root 2. And let's see which option do this satisfy. So type 1, kappa is less than 1 by root 2. Type 2, kappa is greater than 1 by root 2. So this is the option number 1. This one. For question number 2, the correct option is option number 1, that kappa for type 1 superconductor is less than 1 by root 2, and for type 2 superconductor, kappa is greater than 1 by root 2. If this is clear, then let's move on to the third problem, which says that consider the following statement regarding Meissner effect and choose the correct statement. So the first option is the outcome of application of magnetic field is history independent for both superconductor and perfect conductors. Second option is the outcome of application of magnetic field is history dependent for both superconductor and perfect conductor. Third option is the outcome of application of magnetic field is history independent for superconductors but not for perfect conductors. The fourth option is the outcome of application of magnetic field is history independent for perfect conductors but not for superconductors. So let's just deal it. So let me, so this, since this is talking about the Meissner effect, so let me just write Meissner effect first. So it is a defining feature of superconductors. for conductors. When cooled below the critical temperature, when cooled below the critical temperature, in the presence of magnetic field, superconductor expel the magnetic field completely from their interior, and this is not just zero resistance state, but an active diamagnetic response. The important point note here is that the expulsion of the magnetic field happens regardless of whether the field is applied before or after the transition. This means it is history independent. Whether you apply the magnetic field before the material gets superconducting, or if you apply it after, it does not matter. The state remains same. So it is history independent. Now let's look at the case of the superconductors, or the perfect conductors, basically. Perfect conductors. They have zero resistance. That's what the perfect conductor. They have zero resistance, but do not exhibit the Meissner effect. If a magnetic field is present, before the system is in perfect conductor state, the system becomes a perfect conductor. It can get frozen in. This information can get frozen in. So the final magnetic field inside depends on the system's history. This means it is history independent. Sorry, history dependent. What I'm writing. Because it is depending on the history whether the magnetic field is applied before or if the material got perfect conductor or after. So this is history dependent. So for perfect conductors, it is history dependent. For superconductor, it is history independent. So let's look at the option number 1. The outcome of application of magnetic field is history independent for both superconductor and perfect conductor. No, this is wrong. The outcome of application of magnetic field is history dependent for both superconductor and perfect conductor. Wrong. This is also not true. The outcome of application of magnetic field is history independent for superconductors but not for perfect conductor. This is true. And the fourth one is the outcome of application of magnetic field is history independent for perfect conductor but not for superconductor. This is false. The correct answer here is option number 3. That the outcome of application of magnetic field is history independent for superconductors but not for perfect conductors, because for perfect conductors the magnetic field can get frozen in the state, and if you apply the magnetic field before or after, that will be having its history. So it is history dependent for perfect conductor but not for superconductor. Correct answer goes here as number 3. If this is clear, let's move on to the question number 4, which says that choose the correct statement regarding the BCS wave function. First option is the BCS wave function is an eigenstate of number operator. What does it mean? It means that the BCS wave function, in the BCS wave function, the number of kind of a particle will remain constant. Let's see whether it will happen or not. The number of pairs can be fixed by integrating over the phase. The BCS wave function is phi BCS is equals to summation over k uk 0k plus vk 1k. So 0 and 1 are the two states basically. And the fourth option is the BCS wave function is not an eigenstate of the phase. Okay. These are the 4 options. Let's first write down the wave function for the BCS theory, and then we will analyze the options one by one. So the first option is, so the BCS wave function first. The BCS wave function so the BCS ground state is a coherent superposition of states with different numbers of super pairs, and it is given by phi BCS equals to pi. UK plus VK C up K up spin dagger C opposite momentum opposite spin dagger this is the kind of the wave function, and since as you can see it is not an eigenstate of the number operator because there are two creation operator which will change the number of the basically Cooper pairs also. It's not an eigenstate of the number operator, meaning particle number is not fixed. However, one can project onto a fixed particle number by integrating over the global phase. In is proportional to 0 to 2 pi d phi e to the power minus n phi phi BCS. And this is Fourier projection. Which extracts the component with fixed particle number n. Okay, so this is the wave function basically. So the first, now let's analyze the options. The first option says that the BCS wave function is an eigenstate of number operator. So first option is not an eigenstate of number operator. Why? Because BCS states mixes different particle numbers. Second option is the form phi BCS K UK UK plus VK this thing is oversimplified. It is oversimplified. It does not talk about whether the upspin, downspins, and the opposite momenta particles, which makes the Cooper pair. Is oversimplified and does not correctly describe the Cooper pair structure. It misses the actual fermionic creation operator. The BCS wave function is okay. This is also good. Now the fourth option is, the first we have seen is incorrect. Second we are not talking about, because this we already talk about, that the second option is correct. The number of pairs can be fixed by integrating over the phase. This is what it is, the phi n integrating over 0 to 2 pi d phi to the power minus I n phi BCS. So this is correct. Option number 3 is the BCS wave function is 5 BCS. We have seen this is also incorrect. The fourth also we will see. Just give me a minute. So now the fourth option, that the BCS wave function is not an eigenstate of the phase. So the BCS wave function is actually an eigenstate of the global phase, which is why it does not have a fixed number. The conjugate of phase is number, so fixed phase is the number and uncertainty. Basically, they are related. So this is also a wrong option. The fourth one is also a wrong option. The correct option here is number 2, which says that the number of pairs can be fixed by integrating over the phase. Yeah. If this is clear, then I will move on to the next problem, which is question number 5. Question says that according to the BCS means Bardeen, Cooper, and Secrefer. These are the 3 scientists' names. Theory of superconductivity. Which of the following statement is correct? So we have to now analyze the correct statement. Okay. So we know that in BCS theory, okay, let me write. Okay, let's first see the options. The first option is superconductivity is explained by the formation of Cooper pair due to the attractive interaction mediated by lattice vibration, that is phonons. Second option is superconductivity is a result of repulsive interaction between electrons leading to the formation of Cooper pair. Third option is superconductivity is solely determined by the external magnetic field. And the fourth option is superconductivity occurs only at extremely low temperatures and is not influenced by the material's electronic structure. Let's just review the BCS theory of superconductivity and automatically give us the answer. So in BCS theory of superconductivity arises because electrons near the Fermi surface form Cooper pairs which are bound state of 2 electrons with opposite momentum and spin. The key point is they are made by the electrons which have opposite momentum and opposite spins. The second assumption kind of thing is this pairing is driven by an effective attractive interaction with, and which is despite the natural repulsion of Coulombic force, despite the natural Coulombic repulsion. Third is the attraction is mediated by lattice vibration. Lattice vibration is also known as phonon. An that is an electron distorts the lattice, which in turn attract another electron. And this pairing lead to the macroscopic quantum state with zero resistance and other hallmark properties like the energy gap, Meissner effect, and that is we call the superconductivity. And the BCS theory is something which explains this. Now these are the things of the BCS theory. Now let's revisit the options. So according to the BCS theory of superconductivity, which of the following statement is correct? First is superconductivity is explained by the formation of Cooper pair due to the attractive interaction mediated by lattice vibration. That's what we discussed in this thing, right? So this is definitely true. This is correct. Second is superconductivity is a result of repulsive interaction between electrons leading to formation of Cooper pair. No, this is false. Superconductivity is solely determined by the external magnetic field. No, external magnetic field can destroy the superconductivity if they exceed the critical field, but do not cause it. And similarly, in the option number second, repulsive interaction opposes pairing. BCS relies on a weak attractive electron, the phonon mediated basically interactions. Third option is superconductivity occur only at extremely low temperature and is not influenced by the material's electronic structure. This is the first part is true that superconductivity typically occurs at low temperature. It is also strongly influenced by the material's electronic structure such as density of states, phonon spectrum, and the isotope mass. So this option also gets wrong. The correct option here is option number 1, which says that in the BCS theory of superconductivity, the superconductivity is explained by the formation of Cooper pairs due to the attractive interaction mediated by lattice vibrations. Correct option is 1. If this is clear to you, then I'll move on to the next problem. If you have any question, suggestion, you can ask me in the comment section. I will be happy to address your concern. So feel free to ask any question if you have. If there is no question till now, I will move on to the next problem, which is in a type 2 superconductor has a critical field Hc of 5 Tesla at a temperature of 4.2 Kelvin. Calculate the London penetration depth lambda for this superconductor. Hint is given. The relationship between the critical magnetic field Hc, the London penetration depth lambda, and the temperature T for a type 2 superconductor is given by this relation, which is Hc is equals to phi naught by 4 pi lambda square times 1 minus t by tc square to the power half, where phi naught is the magnetic flux quantum, and that is h by 2, which is 2.07 into 10 power minus 15 Tesla meter square. And Tc is the critical temperature. Given that Tc is also 8 Kelvin, solve for the London penetration depth lambda. And answer is should be in the units of nanometers and correct up to the 1 decimal place. This is the problem. Basically, all the other parameters, phi naught, hc, 4 pi, t, tc, everything is given. We have to just extract the lambda. If we can extract the lambda in nanometer, then the question is over. Let's just do it. This is an easy problem. So let me write the given parameters. Hc is 5 Tesla. Temperature is 4.2 Kelvin. Phi naught is 2.07 into 10 power minus 15 Tesla meter square. Tc is 8 Kelvin. And 4 pi everything is we know. So given in the given question, and the question asks about what is lambda. So Hc is phi naught by 4 pi lambda square times 1 minus t over Tc to the power square to the power 1 by half. Lambda is equals to phi naught by 4 pi Hc 1 minus t over Tc to the square power half and square root of everything. Yeah. So this is the problem. We just have to solve it numerically. It's a more of numerical problem than I'll just check whether this relation is right or not. I'm just doubting that it should be hc square. Let me check relation between hc and the and EC for superconductor. One second. Let me just check and verify this equation. is dimensionally correct or not. Hc should be in Tesla. Phi naught is the magnetic flux quantum. Lambda will be in the length. Looks like correct only. So dimensionally looks like it's correct. Okay, so whatever given is there, we will go with that one. So lambda is nothing but phi naught. Phi naught is 2.07 into 10 power minus 15 Tesla meter square times 4 into 3.14 into Hc is Hc here is 5 Tesla. 1 minus T over Tc is 5 by 8 square to the power half. So lambda is 2.07 10 power minus 15 divided by 4 into, I just do the calculator. So 2.07 times divided by 4 divided by 3.14 divided by 5 will be nothing but 0.03296 into 10 power minus 15 times 5 by 8 is 0.625, and if you multiply it by again 625 and 1 minus 0.625 times 0.625, that will be 0.609 times 0.03296, that will be roughly 0.020 into 10 power minus 15 0.60 9375 0.60. Calculator. 0.07 divided by 4 divided by 3.14 divided by 5 multiplied by square root 1 minus 5 by 8. 0. 0.03296. So CE 5 by 8 times 5 by 8 minus 1 times minus 1 to the power 0.5 times 0.03296 is nothing but 0.0257 into 10 power minus 15. In nanometer, it should be 15, so 3 more, so it will be 25.7 into 10 power minus 18 square root. So square root into this is 1000, 5, 25.7 to the power 0.5. This lambda is 5.06 nanometer. Yep. Now moving on to the problem number 7, which is in the BCH theory of superconductivity, what role do phonons play in the formation of Cooper pairs? Phonons are responsible for repelling electrons, creating Cooper pairs. So what exactly happens is these are your phonons kind of thing, and if an electron moves, it distorts these ones because they are also charged, right? They will come like this, and the distortion of the phonons kind of thing, it creates an effective electric attraction potential, and that what lead to the Cooper pair formation. The phonons are responsible for repelling electrons and creating Cooper pairs, but here phonons are responsible for repelling electrons, creating Cooper pairs. No, this is false, because phonons effectively distort the lattice so that the electron attracts the electron, attractive potential. Phonon facilitate the attraction interaction between electrons, leading to the formation of Cooper pair. This is right, absolutely right. Option number 3 is phonons have no impact on superconductivity according to the BCS theory. No, phonons do play a role in the BCS theory. Like if the stronger the electron phonon interaction, then in that case the superconductivity will be easy to attain. And the last option is phonon increase the resistance in superconductors. In normal conductors, phonon do not scatter electrons and increase the resistance. But in superconductors, the formation of Cooper pair via phonon mode leads to, so phonon do not increase the resistance in the superconductors. Number 2, correct here is the option number 2, that phonon facilitates the interaction between electrons, leading to the formation of Cooper pairs. If this is clear, then now let's move on to the problem number 8, which of the following is false about BCS superconductor. So we have to look for the false. This for the BCS theory. So the superconducting property can be destroyed by application of magnetic field and electric field. So this we have seen, right? Strong enough magnetic field Somehow the screen position stopped. So sorry for that. The internet is not very good. So strong enough magnetic field can break Cooper pairs. Via orbital or spin effect. And strong electric field can also affect surface superconductivity. In thin films. Second option is, so this is true. This option is true, but we have to look for the false statement. The transition temperature varies as the atom is substituted by its isotope. Yes, the transition temperature for isotope goes as Tc is proportional to 1 by root m. Right? This we have seen. So changing atomic mass without changing charge affects Tc, confirming the role of phonons. Option number third is that this is also true. The variation of the critical temperature for Becher's superconductor is given by Tc directly proportional to Tc is proportional to 1 over root m, not 1 over m. So this is incorrect. The elastic properties, crystal structure and thermal expansion remain constant as system becomes superconductor. Yeah, this is true because at the critical point where all this transition happen, these things do not change. Thermal expansion, coefficient, crystal structure, elastic properties, they don't change. So the bulk elastic properties, crystal structure, let me write. The bulk elastic properties, crystal structure, and thermal expansion remain constant as system becomes superconductor. So the incorrect option here is option number 3. Now moving on to the problem number 9, which says that a superconducting wire with a critical current density Jc, which is 1.5 into 10 power 7 ampere per meter square, has a cross-sectional area A 2 into 10 power minus 6 meter square. Calculate the critical current IC that the wire can carry. The IC is the critical current. After that, superconductivity will be broken in the system and it will be normal. So JC we know is I by A, cross-sectional area. So I will be nothing but JC times A. I is equal to JC is 1.5 into 10 power 7 into 2 into 10 power minus 6. I is equal to 1.5 into 2 is 3 into 10 equals to 30 amps. So 30 amp is the correct answer for this given problem. Now, if this is clear, if you have any question or doubt, you can ask in the comment section. I will answer that. I will try to answer that concern. If No, then if you don't have any question, then I will move on to the next problem, which will be the final problem in this course. In this assignment, in the course, one more assignment is remaining. So the last problem is, which of the following is the correct expression regarding density of state, ds ek and dn eta k are density of states in the energy range delta about the Fermi level in a superconductor and normal conductor respectively. So delta is the superconducting gap, energy gap basically, and ek is the normal energy. So you have to find out what will be the relation between the density of states. This is a good problem to work on. So I will derive it so that we'll be able to address this problem. So let's start from the normal state density of state. Let's start from normal state DOS. So step 1 should be normal state density of states near Fermi energy. Normal state DOS near Fermi energy. Dn eta k plus to Tn by, okay, where eta k is equal to Ek minus mu is the energy measured from the Fermi level. And we assume it is approx constant near EF. So Dn EF equal to constant. Step 2 is BCS quasi-particle energy relation. In a BCS superconductor, the quasi-particle excitation energy is square plus temperature. This modifies the dispersion from a simple parabolic band to one with a gap delta at the Fermi level. Now, step 3 is superconducting DOS chain rule. We now transform the DOS from being in terms of K to EK using DSEK equal to DN eta K D eta K by DEK. To find D eta K by DEK, we invert the relation, this one, K square delta square, eta K is equals to delta square V square minus delta square. This implies del eta K by del EK is equals to EK by under root EK square minus delta square. Step 4 will be the final expression. We substitute everything. And at EK equal to delta, there will be divergence, 0 inside the gap as expected. So this shows a divergence at EK is equals to delta. The coherence peak and 0 density of state inside the gap as expected. So the final result is DSEK or DNEF is equals to EK upon under root EK square minus delta square 0. EK greater than delta. So EK less than delta will be 0. So let's see which option do match this one. So the option which matches this one is the option number 1. So this will be the correct option for this problem. This is incorrect because here for these regions this is incorrect because of these forms. This is also incorrect. So the correct option is option number 1. So this is the solution of this problem. So to come now, if you have any question or doubt, you can ask me. I will address your concern. If You don't have any question or answer. I will wait for still 10 minutes. If anyone joins the class and have any question or doubt, they can ask me. Wait of 10 extra minutes. Give chance for asking the questions. Okay, right? 10 minutes time. Ask the questions. If you have any question or doubt, you can ask me. I will be answering that question. You can write it in the comment box also. I will be answering that one also. So, if you have any question, just drop a message. Hey Anmol, if you have any question, then ask. If you don't, please turn off your microphone. The class is essentially over. So this 10 minutes time is for asking the questions which has been discussed in this lecture and prior also. So if you have followed the lecture or this one or the previous one and you have any question or doubt, you can ask me. I will address it. And if you don't, maybe you can leave the meeting because this class is over essentially.